Yes.
Okay. So as today's question was pretty well adjusted, so we'll try to discuss it a bit fast. And also, since all of you have attempted a good number of questions, so make sure to put your perspective right here. Try to explain the things because if you explain it here, it will become easier for you to explain in the interviews. So it would be really good if you have got some perspective into the problem, just present it here. It doesn't matter if you are right or wrong, just present it here. And when you are doing, think as if this is your interview. Okay, so try to be more clear, more precise, but don't hesitate to participate in the discussion. Okay, so let's begin. So this was the first problem of today's contest. So you are given a zero indexed integer array battery percentages having length n, denoting the battery percentage of n zero indexed devices. Okay. Your task is to test each device I in order from 0 to n minus 1 by performing the following test operations. If battery percentage I is greater than if battery percentage sorry I is greater than 0, increment the count of tested devices. Decrease the battery percentage of all the devices with indices j in the range I plus 1 to n minus 1 by 1, ensuring their percentage never goes below 0. Okay, so there's nothing more in the question. We have to count number of positive battery charges we have. That's the problem. Okay, but there's one condition, like it will be more clear with this example. 1 1 2 1 3. Okay, so first of all, you get this number. This is a positive number, right?
Huh.
Okay, this is a positive number. So what we'll do is that we'll reduce all the numbers after uh, the occurrence of this one by 1. Okay, so for now, what we can do, like we have got very low constraint here. Like here we have got constraint as 100. So 100 means you can write n to the power 4, or in best case at least n to the power 3, uh, n to the power 3 complexity problems, and it will get accepted. So what we can do, like here we are getting 1. Okay, this is positive number. Now what we'll do, we'll reduce every number coming after this by 1. Okay, now the new array will look something like 1 0 1 0 3. Oh, sorry, 2. Now again we encountered 1 here. Okay, so what we'll do, we'll reduce all the numbers after this one by 1. Okay, so this again is 0. So we won't do anything with 0 because we can't reduce it further to negative battery charges. So we'll move to the next number. So this is again 2. So what we'll do, we'll reduce it to 1. Now our array will look something like 1 0 1 0 1. Now here, how many positive charges we got? We got 3 positive charges, which are this one, and this one. So you need to tell how many positive charges are there in the complete array. So is the question clear?
Huh.
Okay. Now, since the question is clear, now instead of going after every uh, every index of the array, you can just maintain a count variable. So what you will do? Okay, so suppose this is our array 1 1 2 1 3 3 4. Suppose this is our array. suppose this is our array. So what we'll do, we encountered a positive number, so we'll declare another variable called as decrease. Okay. So since we encountered one positive integer, so what we'll need to do, we'll need to decrease all the occurrences, all the positive integer occurring after this index by one. So what will our decrease value become? It will become 1, as every integer next to this integer will be reducing by 1 if it is a positive integer. Okay. Now, at the same time, we encountered one positive battery charge, so our count will become 1. Okay. So now here we got to this position. This is now 1. But is this actually 1? No, because
No.
we have to decrease it by 1. So how will we check this? Suppose we got this variable a of I, we'll decrease it with d. Okay. So after decreasing it with d, if it is still positive, we'll add it to our count. And if it is not positive, we won't add it to our count of answers. Is it clear?
Yes.
Okay. Now let's come to this integer. So here 1 minus 1 will be 0. So since this is not positive, so we will skip this. Okay. We got to this integer. This is 2. So 2 minus 1 is greater than 0. This means we got another positive value. Okay. So what we'll do here, we will decrease all the positive occurrences with minus 1 after this element. So our decrease will increase with 1. Okay. Because earlier we have also reduced 1 from all the elements. Now again we will be reducing all the elements with 1 if they are positive. So our decrease count will increase, and answer in our array will also increase. Now we got this 1. So 1 minus 2, it is less than 0. Okay, it is less than 0. So we won't count it to our answer. Now we got 3. 3 minus 2, it is positive. So this will add to our answer. We'll add it to our answer. And next thing, what we'll do, as this is a positive occurrence, so we'll have to remove 1, reduce the all the positive occurrences of batteries with 1 after this index. So what we'll do, we'll add 1 more to our decrease pointer. So it will become 3. So now again, we'll come to this index. This is 3. 3 minus 3 is 0. It is not positive. We'll jump to next position. Now 4. 4 minus 3 is again a positive. So what we'll do, we'll increase our answer with 1, and also decrease a counter will increase by 1. But after this, we don't have any element, so it's of no use. So our final answer will be 4. And if we go by this, it time complexity will also be order of n only. Is the approach clear?
हाँ भैया.
Okay. So now let's move to the next problem. This is a problem. Okay. Were you able to solve this problem, Chandan?
यस.
Okay. How did you solve this problem?
सबसे पहले मैं ये किया था, इसका पावर कंप्यूट कर लिया था.
उसके बाद मतलब कि ये फर्स्ट एलिमेंट को मतलब ए मान लिया था, सेकंड को बी मान लिया था, और सी करके वो कंप्यूट करके फिर बना दिया था।
Okay, so let's see how we can do this problem. So you are given a zero index 2D array variables where variable of I is equal to a I b I c I m I and an integer target, and index I is good if the following formula holds. 0 is less than equal to I is less than variable's length. So I should be less than variable's length and it should be greater than or equal to 0. So ai to the power bi modulo 10 to the power ci modulo mi should be equal to target. Return an array consisting of good indices in any order. Is it clear?
Yes.
So here what we are given uh, three a 2D array variable, right?
Hmm.
Okay, 2D array of variables where uh, there will be four columns and the number of rows will not be more than 100. Okay, so we can consider this as again uh, we can consider as 100. Okay, so 4 into 100 it's almost 4 it's almost 100 only. Okay, so an index I is called good if the following formula hold. So we have got three array. Okay, so for first we have got this. Okay, these all are what? This is AI, this is BI, this is CI, this is DI. Okay. Now what we need to check? We need to check that A to the power B modulo 10. So let's check. 8 modulo 10 is
8.
8 modulo MI. Okay. So what is MI here?
8 to the power ci 3.
Okay.
8 to the power
8 to the
3
power
modulo
8 to the power
3.
CI.
3.
What is CI?
3.
3. So it is 512 here. Modulo mi. So what is mi here?
10.
Again 10. So it is going to be 2 only.
2.
So here is it clear?
Yes.
Okay. So first of all, how will be okay? The problem is very much simple. Like we have got one array in all the we have got like a array in which every array is a collection of four integers. Okay. So for all the four integers, we just have to apply this formula ai to the power bi modulo 10 to the power ci modulo to the modulo mi. Okay, we will need to apply this formula only for every element, for every element of the 2D array. Now, this is not a problem of complexity in space or time. This is a problem for like setting up the constraint in such a way that you are able to get reach to the answer, right? Because notice here we have got powers, and powers kind of increase the numbers very quickly. So you'll need to be extra cautious when you are dealing with power, right? And although here you are given some relief that the numbers won't be greater than 1000. So this is a very good relief for all of us. Now, how will we calculate the powers? AI to the power bi. Okay, sorry. AI to the power bi. How will we calculate this? Like, do we really need to calculate this at all, or we will be we won't need all of this? What's your thought, Vivek?
I had calculated it, but in the contest with binary exponentiation.
Okay, with binary exponentiation. What about you, Chandan?
यस।
How did you solve this?
फर्स्ट ऑफ ऑल मैं ये किया था मतलब कि ये पावर को कंप्यूट कर दिया था। मीन अगर 2 to the power 3 है तो मैं एक लूप चला दिया था 1 से लेके पावर तक, और देन पावर ये बेस को मल्टीप्लाई कर दिया था कि हाउ मेनी पावर दिस इज गिवन। ठीक है,
Hmm.
उसके बाद एंड एक मॉडुलो भी ले लिया था फंक्शन में। देन फंक्शन को कॉल कर दिया था इस a to the power i करके ऐसे ही किया था।
Okay, so those of you watching this video later, we have already discussed like calculating powers is a bit of tricky thing, and as ex- uh, most of the time it rises very quickly, and very soon you will exhaust the integer limit or even long limit. So what you'll need to do, you'll need to be attentive about the modulo present there. Like here we have got modulo 10. So what does this guarantee? This guarantee that the resulting number can't be greater than 9. Okay, it will be anywhere between 0 to 9. This is the thing. And second thing, what we have to focus on is, again, we have got this modulo. So first of all, there will be a number from 0 to n to the power ci. Okay, we'll need to calculate its modulo, but this can be very large number. But again, we are given a modulo. This modulo is a very helpful thing because again, this number won't be greater than 1000. Okay, this won't be greater than 1000. So when we are taking it all the exponentiation with this modulo, so what this will ensure that our answer won't get any bigger than this 1000. So just we'll use this modulo. And for this, we have in our math section and also in our Astitva batch, Aramba batch of our CP series, it's also present there on YouTube. We have explicitly discussed how to take power with modulo. That you'll need to watch. And if you are watching that video, it will become very much clear. But for those who are not able to find that video, you can directly query us on Telegram or on any other platform, or even if you're watching on YouTube, you can query us. We'll reply it. Okay, then it will be an easy question after this.
I also did the same.
Right. Is the question is very much easy only. You just need to be a bit uh, you don't need to be anything extra. You can just solve it as it is. The question is very easy. And after this, if it is all the adjustment is making it equal to the target, then you include that index also to your answer. Okay. Okay. As here we have to return an array consisting of good indices in any order. So that's it. So now since this question is solved, let's move to the next problem, which is the third problem. And again, I'm telling like this is a very standard contest. This was really very standard contest where every problem were doable. So if you're not able to solve this problem, it's of no, you don't need to take stress. Rather, you take out the problem, spend a good 2-3 hours time on solving that problem. Even if you are not able to solve the problem, just be with the problem. Just spend time with the problem, and slowly you will feel that, yeah, I'm getting the things. And if you're not able to get the thing, you can anyway watch editorial or read editorial. That will help. Okay. So this problem, count subarrays where max element appears at least k times. So how many people were able to solve this problem? Okay, Tanmay and Vivek was also able to solve this. Okay, Chandan, did you solve this problem? Okay, no issue. Let's discuss the approach of this problem. Okay, so here in this problem, what we are given? You are given an integer array nums and a positive integer k. Okay, return the number of subarrays where the maximum element of nums appear at least k times in that subarray. A subarray is continuous sequence of elements within an array. Is it clear?
Yep.
Okay, so here what we have to do, like see, here we have got this array 1, 3, 2, 3, 3. We have got this array. Okay, and which is the maximum element in this array? What is the maximum element here?
3.
3. And what problem is given is that we have to tell count of all the subarrays where the count of the maximum number, which is 3, should be at least k. It can be greater than k, no issues, but it must be at least k times present in that subarray. Is the question clear?
Yes.
Okay. So since now the question is clear, let's see. So here k is equal to 2. So we'll have to tell all the subarrays where 3 is occurring at least 2 times. So this 1, 3, 2, 3, this is a good example. Okay, this is a good subarray, right? Because here 3 is occurring
Yes.
at least 2 times.
Yes.
Okay, now moving to 1, 3, 2, 3, 3. This is also good subarray. Now again 3, 2, 3, 3. This is also good subarray.
Yes.
Okay. Now 2, 3, 3. This is also good subarray.
Yes.
Now 3, 3. This is also good subarray. And 1, 3, 2, 3, 3. This is also a good subarray. Okay. So here we have got all our answers that, yeah, these are all the good subarrays. And what is their count? 1, 2, 3, 4, 5, 6. We have got 6 desired subarrays.
Yeah, you have written 172 times. 13233.
1, 3, 2.
33. 2 times.
Okay. So did I miss anything? Okay, I missed this array. 3, 2, 3, 3.
Yes.
Okay.
No. You have also written that.
I've also written that.
3, 2, 3, 3. Yes. 3, 2, 3, 3.
Okay. 1, 3, 2,
3,
3.
1.
This is one good array. 1, 3, 2, 3, 3 is another good array. Then 3, 2, 3, 3 is another good array.
3, 2, 3.
Okay. 3, 2, 3 we have missed. So 3, 2, 3 is another good array. Okay. So how do we reach to our answer? Tanmay, how did you approach this problem?
So as you just said, this kind of problems are pretty much standard. I mean, this is quite intuitive that this problem can be solved using sliding window. I mean, there are n number of problems such that you would find in LeetCode or GH. So it comes very much intuitively that it will be solved using sliding window.
Okay. What was the approach? How did you approach it?
Okay, so I took 2 pointers, start and end, and then point them in the first index, 0th index.
Okay,
both of
start
them,
and end. Okay.
start and end. And first initialize them with 0 because we are standing at the 0th index.
Okay.
Then we are moving our end pointer. And first of all, we have to find the maximum element of that array, which is 3. So,
Okay.
yeah.
Step 1, we find the maximum element of the array, which is 3 in this case. Okay.
Yeah. Then we have to initialize 2 pointers, start and end.
Okay.
And initialize them with 0. So after that, we'll keep moving our end index one by one until end reaches less than n. I mean, n where n equals to num total, the length of the array, and in between that while and inside that while loop, we have to write a logic where we will count the subarray where the max element, so to say the 3, is appearing at least 3 times.
Okay. So let's dry run on this. So there's one more thing to watch out for. Like here, the constraint is 10 to the power 5. So you won't be able to apply 10 to the n square approach here.
Yes.
So if you're thinking that, okay, one array I'll calculate for, then another else array I will also again calculate. So that won't be possible. Like you may think like that, I'll find all the subarrays. I'll find all the subarrays. So finding all the subarrays will take at least order of n square times, and that won't be feasible here, right? So you have to think a single pass solution only. Single pass, or you can say like order of n solution only.
Yeah.
Okay. So that being said, let's try run this problem with Tanmay's approach. So Tanmay, we have got our start and end pointer both pointing towards the 0th index, and we have found out our maximum element is 3. So let's try run on this problem.
Then we'll keep moving, then we'll move our end pointer by index 1.
Okay.
And while moving this, we have to check if that current element is max element or not.
Okay.
And if it is, then in that case, we will increase our counter variable.
Okay, so let's call the frequency of max element as max f. Okay.
Okay. Now the max element is 1, but to form an array, we need at least k times, where k is equals to 2.
Right.
We need one more time. So we need 3 one more time. Okay. So in that case, we'll move our end pointer by 1, and then check again. And then it is, so in that case, it is 2. So, and also we are in the while loop. So while running our code inside while, we will also check if it is out of bound or not. So as it is not, then we'll keep moving our pointer one by one until we reach a stage where our count I mean the max is k.
Okay. So here our max f is 1, then this is also not equal to max element, so we won't increment our max f.
Yeah.
And this again is equal to the maximum element of the array. So we'll increment our max f to 2,
Yes.
right?
Yes.
Okay, so here we have got one such subarray where frequency of maximum element is at least 2. Okay, good. So now,
Oh, so actually we do not count answer. I mean our count. I mean our
whatever.
subarray count like that.
Okay.
So in that case, we will run a while loop. So
Okay.
if our inside a while loop, there will be another while loop. So if the condition has been met, I mean the max f equals to greater than equals to k, which is in this case 2, then we will keep checking if we can make how many subarrays. Then we'll count. Then we will count how many subarrays we can make using our starting index from the end
Okay.
of our array.
Yeah. So
Okay.
we'll keep the end as this index only,
Yes.
and we'll move the start forward and
No,
check.
no. In first case, we'll not move start. So we'll
No,
check in while loop how.
after we have made our k is equal to, after we have made the frequency equal to k
Yes.
or greater than k.
Yeah.
Then we'll do this.
Yes. Then we'll go inside our second while loop and calculate our count average, which will be eventually answer plus equals to n minus n end, our end pointer. Now the question is why n minus n? I mean that. So in that case, if you see, our start pointer is at first at 0th index and end pointer is at third index, 0, 1, 2, 3, third index. So the first array we can make is obviously 1, 3, 2, 3. But we can also make 1, 3, 2, 3, 3. Okay.
Right.
So yeah. So if there is another element, so we can also include that into our array. Okay.
Perfect.
So that's why we are using this logic. Answer will be our n minus n point.
Yeah. So the logic here is pretty much clear. If we are getting 1, 2, 3, 3. Suppose this is our array. 4, 4. Sorry, no, 4. 1, 1. So here, suppose k is equal to 2. So by this time, we have reached k is equal to 2 for the maximum elements. So if we include further more elements like this one and another one, then also we can say that if our k is meet, like for the maximum element, it is occurring at least k times, then after including these also, it will be present at least k times, because we are not removing an element, we are adding an element. So at least k condition will remain maintained only, right?
Yes.
So perfectly, we'll do this and we'll add n minus e. If k is greater than or equal to, sorry, if, yeah, the count of the max f is greater than or equal to k.
So we'll keep doing that while our max f is not less than k. Okay. And if our k by any chance goes less than k, then we will break the while loop and we'll keep moving our endpoint.
Okay, so
So
initially our n is here 5, and when we encountered our first k is equal to 2 condition here, so 5 minus 3, these two arrays are possibility, right?
Yeah.
So we'll add them, and then again our s will move to this position, right? S is equal to 1. So here again we have encountered the same element as the largest element.
yes,
So we'll need to decrease its frequency first,
yes.
right? We'll
Yes.
decrease its frequency. So
No,
when
no.
we
In that case, we will not decrease our frequency because our start pointer is now at pointing at 3.
right. So we'll start pointer is at here.
Yes.
Okay. So 3 to 3.
It
Again
will
we have
start
got
at,
k,
yes.
right? And again here we'll add s minus end. So sorry, n minus end.
E. Yes.
Right. So what are the two arrays which we are including here? We are including 3 to 3,
3 and then 3 to 3 3.
3 to 3 3.
Yeah.
And which two array we included here? We included 1 3 2 3 and 1 3 2 3 3.
Hmm.
Perfect. So now we'll move our start pointer again to this index.
Yes.
To this index we'll move.
Yes.
Now here, what is the condition? Now since we were moving from this element, like we were excluding this element from our subarray. So this was contributing to our frequency of maximum element. Now as we are removing this, our frequency of maximum element will decrease, and as it will decrease, it will become equal to 1. Now it is not equal to k. So once again, we'll need to add more elements to our subarray to make it equal to
K, at least K.
right, at least k. So again, our start is here, our end is here, and now k is equal to 1. So again, we'll move our end here as we have moved our end here. So now again, k becomes, max frequency becomes equal to k, which is 2. Okay. So now here end is at 4th index and n is 5. So 5 minus 4 is equal to 1.
1.
So which array we are adding here? We are adding 2 3 3. So okay, this is one such possibility, and we'll add it to our answer. So our answer now becomes
5.
Okay, our answer now becomes 5. 1 and then 2 2 we have added till now. Now again, as it our frequency of maximum element has become equal to k, so we'll adjust our starting pointer. So we'll adjust our starting pointer to this index. So since this was not 3, we'll not decrease the frequency max f. Now again, k remains our frequency remains equal to k, so we'll add another n minus e, which is again 1. Now again, let's move our starting pointer. So our starting pointer will come here. Now as our starting pointer has come here, again the frequency reduces and it goes less than k.
Yeah.
And as it has gone less than k, so we won't count another array.
We'll break out of the inside the second while loop, and we'll keep moving our endpoint. And
Right.
and in that case, we'll be out of bound. So we'll also move our outer while loop.
Right.
And break out from our outer while loop, and we'll print the answer.
Right. So I hope you would have understand this solution. So Chandan, is it clear?
Yes, clear.
Okay.
They already solved.
Okay. So So now let's move to the next problem, which is the final problem of this contest. It was not very easy, but at the same time not very hard also. It was using the same permutation and combination concept, which we have been discussing for past 2-3 classes at least, right? We have been discussing about permutation and combination, which one to take, which one to not take, right? So let's get into the discussion of this problem and let's try to solve this. So Tanmay, were you able to solve this problem?
Actually, I partially solved.
Okay, you partially solved. And what about you, Chandan? Did you solve this problem?
No, I have not solved.
Okay. So I hope you all have given enough time on this problem, because this problem is quite a good problem only. If you will give good time on this problem, you will be eventually able to solve this problem. So, okay, Vivek, are you still there in the meet? Your mic is unmute, but your voice is not coming. Okay, let's move and read this problem. If Vivek, you're still there, then do join in. So you are given a zero indexed array nums consisting of positive integers. A partition of an array into one or more contiguous array is called good if no two subarrays contain the same number. So this is the problem statement, pretty much straightforward. Return the total number of good partitions of nums. So here, what is the condition? The condition is very much clear. So let's try on this third example. Let's try on the third example. So the condition is very straightforward. You have to partition the array into good subarray such that no two subarray contain the same number. Like, see, if we put all, suppose 1, 2, we made this partition and we make another partition as 1, 3. So this is a good partition. No, this is not a good partition. Why? Because here in first subarray also 1 is occurring, and in second subarray also 1 is occurring. So we need to be pretty much sure that we want to include we need to include all the occurrences of an element into a single subarray. If we are including 1 in this subarray, then all the occurrences of 1 should be present within this subarray. Now suppose if our example was something like this, 1, 2, 1, 3, 1, right? Then we'll need to take all of these into consideration. Is it clear? If we have to include 1, if we have to include this one, then we'll also need to include up to this one. Is it clear, Tanmay, Vivek, Chandan?
Yes.
Clear.
Okay. So now and here we don't have this obligation. Like we can also choose not to include this one. If we don't include this one, then what will happen? If we don't include this one, then we'll partition. We are not including all the one in the single partition. Like we are partitioning this one as separate. So what will happen? So we have partitioned this one into one subarray. Now where all the other ones will go? They will also remain in some other subarray. Now, as our another ones are also there, but not in the same subarray, it means that this partition is not good. So one thing we need to be again very much clear that we need to include all the good partitions, all the elements in a single partition only. So let's take a bigger example, then things will get even more clear. One, two, three, one, then let's take 4, then 7, then 5, then 6, then 7, then again let's end this here only. So what is the number of good partitions here? Let's try to calculate this. You all are still here, right? Tanmay, Vivek and Chandan?
Yes.
Yes.
Okay. So now let's try to solve this. So here, if we are including 1 in our first partition, we have to include 1. We have to do at least one partition. One partition is always a possibility where we will include all the elements of the array in a single subarray.
Yes.
In that way, we don't have any other subarray, so there won't be any other repeating element. That's a guarantee. So one answer is always possible, where we include all the elements of the subarray into single array. Now, that is always a possibility, so answer will always be at least 1. Now suppose we have to include this one. So if we have to include this one, we will need to include, okay, let's remove this 7 also. Instead, let's keep it 5. If we have to include this one, we'll need to include all the remaining ones also in this partition, in this subarray. So if we are including this one, then we'll need to take all the elements up to this index in this subarray, because the last occurrence of 1 is at this index. So if we are including this one in this partition, then another one should end here only, should come in this partition only. Is it clear?
Yes.
Now this is one good partition. Now for again, let's come to 2. So 2 is occurring here only. So no, 2 is not causing any issue. Like 2 is occurring only one time, so we don't have to bother about 2. Right? Now let's see about 3. So 3 is again occurring one time only. One time only, na?
Yes.
So again, we don't have to worry about 3. Now again, this one we have again counted only. It is occurring in this subarray only. Now let's come to 4. So this is a partition, like we can say that 1 is not occurring anywhere else in the array. Now let's come here to 4. Now 4 is occurring here. After this, no 4 is there. So we can say that we can put a partition here also. Like our first subarray will be 1, 2, 3, 1. Our second subarray will be 4 only. Can we say it like that? Because there is no other occurrence of 4. At the same time, what we can do is that this is also good subarray. This is also good subarray. We can also merge them. 1, 2, 3, 1, 4. And our final subarray will look something like this. This is also valid partition, isn't it? Okay. Now let's move to the next element, which is 7 here. Okay, now 7. 7 is occurring only one time here in this array.
Hmm.
So what we can do? We can count 7 as a separate array,
Yes.
or we can merge 7 with the previous good subarrays. So which were
Yes.
4 and 7. We can merge like this, or we can merge with this. The
Yeah.
final subarray will look something like 1, 2, 3,
4, 7.
1, 4, 7.
Yeah.
Okay. Now again, these are all the possibilities. Now let's come to this 5. So we have counted we have calculated all the answers till this 7. Now let's come to this 5. So here, for this 5, is this 5 occurring only one time?
No.
No. This 5 is not occurring only one time. This 5 is occurring twice,
Twice.
right? So what we'll do is that if we are including this in a subarray, then we'll need to include up to the last occurrence of 5 also in this subarray,
Yes.
right? So our subarray will become something like 5, 6, 5. Okay. So again, what are all the good partitions here? 1, 2, 3, 1. This can be one partition. Then 4 again can be another partition. 7 again can be another partition. Then 5, 6, 5 can be another partition. These are all, this is a good partition. Like here, every element, we can say that in every subarray, every element occurring is unique. Like you won't find another 1, 2, or 3 in any other subarray. You won't find another 4 in another subarray. You won't find 7 in another subarray. Okay. You won't find 5 in another subarray. This is a one good partition. Now again, what we can do? Can we merge two good subarrays?
Yes.
Yes.
Yes. So by this way, we'll reach to our answer. So what all we can do? Can we merge these two?
Yes.
Okay. Can we merge these two?
Yeah.
Right? Can we merge these two? Yeah, we can merge.
Yes.
Yes.
Okay. Can we merge these three? Yes. Can we merge these three? Yes. Can we merge these four?
Yes.
Right? So simply in the same way, we'll need to calculate our answer. So is it clear?
Yeah.
Hmm.
Clear.
So now, how will we calculate this? Vivek, how did you calculate it after this?
Like from this, we can conclude that the number of partitions.
We got the number of
We will
partition, right?
uh, now the total number of subarray will be 2 to the power of number of partition. Like
Total number of,
not calculating exact, like eh, the positions where we can we have to just calculate the position where we can separate, like
okay,
the one
okay,
less
okay, I'm
than.
getting you. So there's a, okay, Vivek, can you just put yourself on mute? Some sound coming. Okay, stop. Okay. Sorry. Our example was 1, 2, 1, 3. What was our example? Does
1, 2,
anyone?
1, 3, 4, 7, 5, 6, 5.
4, 7, 5,
5, 6, 5.
6, 5. Okay. So I think it was not 3 here. 3 was somewhere here.
Yes, 1, 2, 3, 1.
Okay. Okay. So I hope all of you must have read this very standard PNC problem, balls and sticks. Like what we have to do, 1, 2, 3, 1. Okay. And 4 and 7. Okay. 5, 6, 5. These are all the good partition which we can make. Now, what we can do? We can put a partition here or not put at all.
Yes.
Here. We can put a partition here or not put any partition here at all. We can put a partition here or not put any partition at all here, merging the remaining elements. So how many options do we have? Either we can put this or not. Either we can put this or not. Either we can put this partition or not. So total, how many options do we have of partition?
2
from this, 2 from this, 2 from this. So total it will be
2 to the power total 3.
total number of partition which we can make.
minus 1.
Right, right. So one thing you have to notice is that after this, like after you have made n minus 1th partition, you don't need to put a partition line at the end. Right? So that is already counted in your solution. So you don't need to put a line to the end. So you'll only need to do partition for you'll only need to put n minus 1 or p minus 1 partition lines.
Yes.
Okay. So now let's come and solve this. Like this is again solved only. So here p is 4 minus 1. 2 to the power 4 minus 1 is 2 to the power 3, which is 8. So let's solve another example. Here again, so these example were like not very good. So here we have got 1, 2, 3, 4. So 1 is occurring only one times, 2 is occurring only one times, 3 is occurring. All of the elements are occurring only one time. So we can either put our partition here, here, here. So with all of these, we have got two options. Either we include this partition or we don't include this at all. Again, we either include this or not include this at all. Same, either we include this or not include at all. So total, how many options do we have? 2, 2, 2, and the total will be 8. And this is our answer. Right? Now let's come to this example. 1, 1, 1, 1. As we know, if we are including 1 in a subarray, then all the occurrence of 1 should be in that subarray itself. So we'll include all the elements to this, the last element, as the last one is at the last element, last index of the array. So we are able to make only one partition, like that is the complete array only. So it will be 2 to the power number of partition, which is 1 minus 1. It is equal to 2 to the power 0, and it is equal to 1. Now let's come to this example, the one with which we started. 1, 2, 1, 3. So this 1 to 1. If we are including 1, then we need to sure that if we are including this one in our subarray, then we'll also need to include the last one in our subarray if we are including the first one. So this can be one partition and another will be 3. Okay, so either we can put this line or not put it all. So total options, how many? 2. So this is a simple problem. Now how do we calculate the last occurrence of an element? That we can do simply by maintaining a hash map. Yeah. So we can do simply a hash map, like yeah, that thing is I think very much clear. I won't like that you'll need to think on yourself. How will you, like every time you are getting an element, like if you are getting this one, okay, so last occurrence of 1 will be 0. Now again you are getting 2, so last occurrence of 2 will be, last occurrence of 1 will be 0 here, then last occurrence of
So, Bhaiya, can we use binary search, I mean, the lower bound to
the array is not sorted, right?
find? Oh.
Okay, so last occurrence of again 1, so again we are getting 1, so last occurrence of 1 increases to 2. Now again we are getting 3, an unique element, so it will become like this.
Oh, we
So
can put them each element into our yeah set, ordered set. I mean, even unordered set also. Then inside that set we can use lower bound. I guess
why do you want to use lower bound? We are doing it in order of n complexity.
10 to the power 5, right? So can't we use n log n?
If we are solving in order of n, why do you want to solve in order of n log n?
And I thought, I don't know.
No, we can even include further complexity, but this is simpler.
Okay.
Like we are just iterating to in the whole array, and we are just getting the last occurrence of every element. And if we are including the first occurrence of an element, then we'll also need to include till the last occurrence of that element. That all we need to do, and rest all thing will be taken care of. So we'll try and find out all the good partitions which we can make, and then we'll calculate our answer as 2 to the power p minus 1. And again, there is a good possibility then that you can get a out of bound exception. So for that, what you'll need to do is that you'll need to keep an eye on the modulo, which is given here. It is 10 to the power 9 plus 7. Now again, we have discussed in the first problem, or sorry, second problem itself, that whenever you are doing power or even multiplication in the case, you need to be very much cautious, because there's a very sure shot chance that you can encounter a integer overflow. And last time also, Tanmay was telling, like, he also got an integer overflow exception. So whenever you are doing multiplication or taking a power, there's a very good chance that you can encounter an integer overflow exception. So to cater that, what you'll need to do is that you will either take long, or you'll need to be attentive of modulo given in the problem. So here we are given modulo. So whenever we are taking power, we'll be using this modulo. And again, this how to take power, how to find power of certain number with modulo, that we have discussed in some detail in our maths playlist of Arambh, or even of placement preparation series. So if you watch it, the things will become very much clear.
I have pasted the code in the chat.
Right.
The power.
It is not showing up here.
Refresh this.
Are you guys able to see? Chandan, Tanmay, Chandan, Vivek?
Yes.
Okay, so it's not coming for me. If you are able to see.
Let me paste it again. Okay, can you see now? Yes, Vivek has also Paste it.
Now Vivek's one is coming. So again, this you can do, not a big deal. This is based on a simple logic which we discussed now. Okay, sorry, this is the power function. Yeah, so this is the power function which we have again discussed quite good number of times. So I hope the discussions were clear, and all of you, those who were not able to solve the fourth problem, do attempt to code it, and it will be easy only. But if you are not able to code this problem, then do tell. We'll try to code it together, right? And this week again, we'll be discussing the code chef contest, and also we'll discuss this week's bi-weekly contest which occurred yesterday, or we'll see if we discuss the latest code forces contest of this week. So again, that will be told beforehand.
ये कोड प्रोसेस का क्वेश्चन हो नहीं रहा है, इसके लिए क्या करना पड़ेगा?